I met him also at the Speciv conference a year and a half ago, he heard my talk and liked it, which is cool. But anyway, we were going to have him bring a demonstration. He's been working on a cavitation device now for, I don't know a few years, and has been making some tremendous progress. I don't know, those of you may have heard of cavitation-induced infusion before, cavitation-induced fusion, excuse me, and perhaps have heard that it doesn't work and things like this. I think after today's talk, you'll feel otherwise. But there's a short story on this, and that is that we were actually going to have him bring a demonstration here today, and we went back and forth trying to get this thing here. And the end result was we weren't able to pull it off, which is too bad because it's pretty impressive, and you'll be learning more about it. But next year, so this is your claim, we'll have this baby to show in Minneapolis. So I'd like to bring up, and one other last thing, this is the paper last night, if you may recall, that won our in-house little vote as to which we thought was the best paper in the proceedings. This is the paper that won. So I'd like to introduce Dr. Max Fomitchev-Zamilov.
Well, good morning, everyone, and thank you for the opportunity to speak to this fine audience. So what I'm gonna do, I'm gonna tell you about the research in cavitation-induced fusion that we do as a part of our corporate activity under the auspices of Quantum Potential Corporation. A little bit about myself. For the past 8 years, I have been researching alternative ideas in physics, and like you, I hold an opinion that a lot is screwed up in mainstream science. But the only way to prove mainstream science wrong is to do something repeatable that works all the time when you push a button, and something you cannot argue with. So upon looking at a bunch of projects, I picked cavitation-induced fusion because it is based on science and physics that is conventional, that is well understood. So what is unusual about it is conditions under which fusion can happen. So this is not cold fusion, this is traditional hot fusion, but the necessary conditions are different. And the reason I picked this project is because it's easier to construct something that you can actually understand. So if you talk about cold fusion, nobody understands cold fusion. There is no theory about, how can you do an experiment on something you do not understand? It's going to be very, very difficult. That's why it's taking 20, 30 years, and no repeatable experiment exists. Well, not so is bubble fusion. Okay, so basically, I don't want to take a lot of credit for any discoveries. We basically stand on the shoulders of giants. Other people have done the bulk of the work, developed theories, and discovered interesting phenomena that has largely remained obscure. Because the second you announce that you can do fusion on a desktop environment, all the big fusion groups, like Princeton Plasma Physics, National Ignition Facility, feel threatened that now their bread and butter is going to be gone. So they do everything they can to thrash the emerging idea. So this is pretty much what happened when bubble fusion papers were published. But the idea is to build a power generator, obviously that's going to displace fossil fuels. It's been 21st century now, and we're still using coal and gas and oil. How long can this last? We should move on to something better. So what fusion is you take deuterium and tritium and you smash them together to create helium-3, or helium for that matter. What not many people realize is the only viable power source that can displace existing power sources has to be nuclear in nature, because there is so much energy density in nuclear matter, it's unbelievable. So 10 micrograms of deuterium are equivalent to a barrel of oil. 10 micrograms. Can you picture such a minute quantity? So it enrages me hugely when I see the government investment into wind, solar, other types of renewable energy that is pissing in the ocean. There is no energy density available in this renewable energy. There is no energy in the wind. There is no energy in the sun. But look at the nuclear energy. 10 micrograms is a barrel of oil. This is what we should be looking at. So why fusion? Well, because it's tremendous energy. So the beautiful part about fusion as compared to fission, fission is also nuclear energy, right? But fusion does not produce radioactive isotopes if it's done correctly. Granted, there is a neutron flux, but if neutron flux is properly moderated, it's not going to induce any radioactive transmutations. So that's why fusion has been pursued by government for 40-some years, and who knows how many tens of billions of dollars were spent. But there is a consensus that fusion is a clean energy, and because we rely on deuterium, deuterium is found in water, and it's so much of it, it's unbelievable. So it's an inexhaustible resource. So the trick is to do it. So because fusion was so important and government spent so much money, we wonder, what the hell happened? 40 years ago, everybody thought it's going to be 5 years from now, and every year we hear it's 5 years, 10, 20, 50 years from now. So every year it's still 50 years from now. Why? Well, because when the whole fusion business started 40 years ago, scientists convened and figured, well, we'll do magnetic confinement, and as an alternative, we're going to do inertial confinement. And one of these approaches is bound to pan out. Little did they know that they will run into crazy, difficult technical issues along the way. And those issues still not resolved. But what happens after years of research, the projects became too big to fail. They have communities grown around them with hundreds, if not thousands of scientists employed. So now you gotta say, well, gee, that approach was wrong, we gotta scrap it. So this was all for nothing, and people just don't have guts to do it. So we cannot let go of our failure. And unfortunately, this is what's happening. And whenever you come up with an idea that's going to displace this too big to fail projects, well, people aren't too happy to hear about it. So I called it novel idea here, but it's not really novel idea. Cavitation is the process when bubbles form in liquid under the influence of extreme pressures and extreme acoustic vibrations. You can have bubbles form in liquid. So what is remarkable about those bubbles, and when these bubbles collapse, they focus energy. They focus energy so greatly that metal is eroded easily. Temperatures within bubble cores raise to tens or hundreds, thousands of degrees, and plasma is formed. So it's really, really energetic process. So you cannot see those bubbles; they're so small, but you can see the effect that those bubbles make. Metal is eaten away. So, because these bubbles focus energy, this gave people idea, what if we can focus enough energy, just enough to cause fusion? So in fact, theoretical papers has been published in prestigious journals that spoke about the ability of just engineering just the right bubble. The right bubble is going to focus enough energy to where the core temperature is going to rise briefly to millions of degrees, and that will be sufficient for fusion. So a bunch of papers have been published, and scientists argued about it and generally accept the theoretical possibility. And this theoretical possibility inspired seven groups across the globe, mostly in Russia and the US, to do experiments. And those 7 groups actually succeeded and published their experimental results, which I'm going to discuss briefly. The best known work is by Talyarkin, who initially was at Oak Ridge National Laboratory, where they published their seminal paper in Science about fusion occurring within the collapsing bubbles, and then he got hired by Purdue, because Purdue thought, well, this is going to be the next big thing. How about we hire this guy and we reap the benefits of delivering fusion power on a desktop environment to the world. So here is Uzi Talyarkin. Like many scientists that were mentioned in this conference this past few days, he was punished for being too enthusiastic about what he has achieved. But to give a fair account, he was his own enemy as well. So it happens often when you discover something great, you think you're going to make huge money quickly, so you withhold important information. So in papers that he published with his co-authors, he withheld important information which precludes other scientists from reproducing his results easily. So when competing groups try to reproduce his results, which is the hallmark of scientific acceptance, somebody has to reproduce your results. So, but when you have a paper that's missing key critical detail, other people cannot reproduce it, they say, well, it doesn't work. And because of vested interest in conventional hot fusion, a war broke down between Ruzi Telyarkin and some of his opponents. And that got pretty nasty and pretty soon escalated into Bubblegate scandal. As a result, Purdue lost all of its nuclear faculty because nobody wanted to be associated with a scandalous environment. So everybody's left. Ruzi was stripped of all of his academic achievements that could be taken away except for his professorship. So cannot do any more research in bubble fusion, cannot even have graduate students for that matter. So he's all but destroyed. Why? Because he published a paper where he presented results of successful experiment. In fact, it was a series of papers. But little is known about similar research that was performed in Russia. In fact, when Telyarkin published his famous paper in Science on bubble fusion, Lipson, who is my compatriot, came out and said, but we did this 10 years before Telyarkin. We did this in Russia. We used a titanium sonotrode that you can see here. And we used deuterated water, and our bubbles were formed on the surface of titanium, and when the bubble collapses, the reentrant jet is formed, and it pierces the titanium deuteride layer on the surface of sonotrode, and that compacts deuterium and causes fusion. But nobody knows about Lipson work here. Very few people do. But he's not the only one. So Biturin team at the High Temperature Physics Institute did similar work about the same time as Telyarkin published his paper. So what they did, they used a gas chamber. So what you're looking here is a gas chamber through which, not a liquid chamber, through which a bunch of gas bubbles were traveling. And they used a wire and a capacitor, high power capacitor. So capacitor was discharged and was launching a high current into this circuit. So this circular wire was exploding, launching a shock wave and compacting the bubbles basically to nothing. And the bubbles, of course, were deuterium gas bubbles and deuterated water. And they detected, huge neutron emission. I actually traveled to this institute and I spoke to the people and begged them to reproduce the experiment for me. But a few years have passed, key people have left, some have gone crazy. So that was unfortunately impossible to reproduce. But it's, whenever you want to take an experiment and repeat it, you have choices. Do you go with Telyarkin's work? Do you go with Biturin's? Do you go with Lipson's? So I decided to go with Smorodov's. This is another Russian, my compatriot as well, who did a particularly elegant experiment. So I did approach Telyarkin 2 years ago and his colleagues and said, look, if I find money, let's, would you help me recreate the experiment to where we settle this controversy once and for all? And the answer was, yeah, sure, we'll help you. You just pay our rate, which is $500 an hour, and we'll work with you to recreate it. And then the bill of materials and effort was so huge that I said, no way I'm going to spend, $1 million on an elaborate experiment. This is like a Cadillac of unnecessary complexity. So this is a much more simple experiment. So the difficulty of Telyarkin's experiment was resonance. So whenever you build resonant hardware, you have to tune it. 1 out of 10 pieces works. Basically, build 10 resonators, discard none. 1 may work. So a lot of fine-tuning issues. That's why it's so expensive and so hard to make. But in Smorodov's situation, it's rather elegant. So all we have is a chamber that is filled with glycerin. So inside here, glycerin, then you have a needle that feeds a bubble. It's a single deuterium bubble. And it's rather large. It's maybe like centimeter in diameter. And then you have a piston, and you drop a huge weight on the piston rather quickly. That launches a shock in the glycerin. The shock compresses the bubble. Bubble focuses energy if the bubble size is right, and if your pressure is correct and the rise time is adequate. The core of the bubble briefly will heat to 10 million degrees, and because of a large volume, there will be a large density of ions. So you have finite detectable probability of fusion, and this is in fact Smorodov's data on neutron yield. So here we have impact energy. So about 450 joules of energy applied to this piston, all is necessary to produce neutron emission far in excess of background. So unfortunately, Superanos died a few years ago, so I had to find all of his available publications, and I chose this as the starting point for our experiment. And this is, by the way, Telyarkin's experiment. So Telyarkin was criticized for actually employing neutron source in his experiment. So his liquid was so pure and there were no bubbles in that liquid. So how the hell do you make a bubble in a liquid which is pure? So he used neutron source, sort of punch holes in the liquid to nucleate bubbles. And then the critics said, well, it has neutrons in the experiment to begin with. And neutrons are telltale signs of fusion. So later he transformed his experiment to where there were no neutrons in it. At least no neutron source in it, but neutrons were still generated. So to summarize, the idea behind cavitation-induced fusion is quite conventional. So it's textbook physics, no cold fusion. So there is solid theoretical foundation that's been developed by about 10 to 20 scientists. About 4 successful independent experiments, 3 out of which were performed in Russia. So when you present this information to mainstream scientists, they are not aware that research has been done in this field in Russia, so they know only about American publications. So when they say, Telyarkin work, it was bullshit. This is incorrect because other people have done it, and nobody bothers to go through all the details. But long story short, how about we actually do it? And we prove that this is not bullshit, this is working. So we started properly. We started with mathematical model. So we processed a bunch of papers, got all the formula that we needed to model the bubble collapse, how pressure and temperature and density is going to behave. And we have a Mathematica model and a MATLAB model that tells us what are the conditions inside the bubble. So that model is the first step in telling you what size of the bubble you need, what pressure you need, what concentrations of gases you need. So from that point on, you can start designing an experiment. But a model is a model. Reality is different from a model. So an improvement, a step-up improvement from that model is a molecular dynamics simulation. So you can write a molecular dynamics code and see how atoms will collide, how shock waves are formed, what the temperature, what the ionization level will be, and we've done all of that. So we have a computer simulation of the entire process. Now, from that on, we proceeded to starting experimental work. We've designed 3 experiments and prototype hardware. But first of all, about necessary condition. You can create a bunch of bubbles, but not all bubbles are going to result in fusion. So how do you know what conditions you need? So first and foremost, the bubble collapse has to be supersonic. So the pressure has to be so high that the bubble wall moves faster than the velocity of sound in the bubble gets. What that does creates a shock. Because bubble is spherical, the shock is spherical. The shock converges in the bubble core. It's almost singularity. It's high density, high pressure, high temperature. This is a necessary condition for fusion. So the collapse has to be spherical, or your shock is not going to be spherical when it converges. And of course, the vapor pressure of liquid has to be low, otherwise the bubble is going to fill up with evaporated liquid and you will not be able to get the pressure that you want. So what you see here is the results of our molecular dynamics simulation. So here is the starting conditions. So we couldn't model the entire bubble, so we modeled just the conical section of the bubble. So you start, and here's your bubble wall. As bubble wall starts moving inward, see the atoms that collide with the wall heat up, hence the red color. And they also clump together, so the shock starts to form. So at some point, the shock becomes very well defined, and even when the bubble stops converging, collapsing, the shock keeps traveling towards the bubble core, and it focuses within the bubble core. So this is where you get the high temperature, high pressure necessary for the fusion. So we've conducted several experiments to test, Telyarkin's and others, his co-authors and other groups' results. And what you're looking at this picture is our single bubble experiment that was after Superanos. So here you see the chamber that was made out of plexiglass, and within that chamber is a needle for gas injection. So piston goes up here, and here's the weight. So it's a 200 weight. Here is the weight. It's not inserted into the shaft. So 200-pound weight impacts the piston that you see there on the table that's normally inserted, and creates a shock in the glycerin that compresses the injected deuterium bubble. So we ran this experiment about 10 times. On the first 3 tries, we got neutron emission that was way above background, which was very encouraging sign for us. But the trouble was, after the 10 experiments, we broke the system. And ever since, it's been in repair and disrepair. Fortunately, we've redesigned the system and almost ready to resume our experimentation. So, it sounds pretty simple, but when you start doing something like this, weird problems creep up. Your bubbles do not blow, your needles bend, your system leaks, your weight does not strike the system quite right. It's, petty little problems that you need to overcome. So it took us about 6 months to sort them all out. Now we're ready to resume that part of the work. This was our previous experiment that was modeled after Telyarkhan. So what you see here is a small chamber. In Telyarkhan's case, it was made of glass, and it was breaking all the time, so we made it from metal. And here's an ultrasonic transducer that creates acoustical vibrations within the chamber. So you see our deuterium supply system, and deuterium is injected, deuterium bubbles are injected, and bubbles are oscillated by the transducer. And the transducer is driven by a power amplifier, and behind you see a neutron detector. So that experiment was not particularly successful. It was the experiment that we started with. We realized that Telyarkhan's setup was too cumbersome, too difficult to do. You needed to collect a lot of statistics on neutron detection. There are background neutrons. So how can you tell that the neutron that you detect coming from your experiment or are they background? So you need to collect a lot of statistics. And then when people come in and say, well, your statistics is off. So ideally what you need to have is neutron emission far above background. So that's why we dropped this experiment and went to Superanos setup, which is this one, because that gives neutrons far in excess of background. So you get a spike, and nobody can say, well, that's background. And this is what you want. In a field replete with skepticism, you want to have result that's incontrovertible. Every time you push a button, you should have a neutron signal far above background. In parallel, we've been designing the commercial reactor prototype because you cannot sell this idea to an investment community if it's just a scientific curiosity. Just to prove that we're smart, we can do this. That's beside the point. The idea is to improve the life of people. Global warming is here, how long can we rely on fossil fuels? So we've designed a commercial reactor prototype that is based off hydrodynamic cavitation that we indeed wanted to bring and show here. And I promised to Greg now. So next year he's going to be here and it's going to be working. So what you're looking at here is inside of the reactor. You see the impeller, and what it does, it pumps the liquid. So whatever liquid you use, doesn't have to be water. In fact, water is terrible liquid. So there are some better liquids that are proprietary that we use. So the liquid is pumped, and the rotor that sits on the impeller creates variable acoustic pressure. So you also need to inject bubbles in the system, so the bubble supply system is not shown. So when bubbles are injected, rotor makes them vibrate. They expand and collapse, and if the bubble engineered properly, guess what? You get fusion reactions in the bubbles, and these fusion reactions give off heat, so the whole liquid heats up. So from this system you can build a power plant. Basically, your liquid circulates, the liquid is enriched in bubbles. Bubbles produce only 10 to 20 fusion reactions, but because there are billions and billions of bubbles, the energy that they produce really adds up. And because they oscillate frequently at the rate of several tens of kilohertz, you can get about 10 kilowatt from a liter of liquid. So 10 liters is 100 kilowatts. So our volume is about 10 liters, and we're shooting for a 100 kilowatt generator. So what you can build is a power plant that's very similar to a conventional power plant, except you replace, let's say, uranium rods with a cavitation-induced fusion system. So to summarize what we have to date is we have an analytical model that we also verified with molecular dynamic simulation. So two models give the same results, so it gives us confidence we're on the right track. Now we detected neutrons in our experiments, which is a telltale sign of fusion. We've designed a commercial generator prototype. Now we need to repeat our experiments a bit more carefully and refine them in a way to where we can push a button and we get a neutron and it's undisputable. So this is what we hope to accomplish by the end of this year. So the goal for us is to demonstrate fusion. Push a button, get neutrons. Nobody can dispute that. Once academia validates, and we cannot disregard mainstream. They have all the powers. You have to go through the pain on convincing them, and they will be convinced when they see a neutron emission coincident with push of a button. When the system actually does something, bubble collapses. Now we already have good ties with AECOM, which is a large engineering company, because one of their VPs is an investor in our company. So as soon as we have a repeatable fusion, the engineers will be able to validate our results and say, yeah, these guys aren't crazy, it really works. And from that point on, it's a pretty straightforward plan to engineer the system that's going to produce sufficient power that's going to be of commercial interest. So brief roadmap. For this year, we will demonstrate single bubble fusion. Next year, it's going to be a process control demonstration. So okay, one bubble works. Can we extract more power from it? That will be the objective for the next year. After that, can we extract so much power that it's going to be more than the power required to drive the experiment? You need power to pump, you need power to create acoustic vibrations. So if all goes well, I think this is going to be a project that's going to span 3 to 5 years, and it's going to require between 10 and 50 million, which is still chump change compared to conventional fusion projects. The trouble is the financial community wants to have something that is ready. Bankers and investors somehow miraculously think that scientists, enthusiasts are going to create the next big thing in their basements without requiring any funds, and it'll come to them to ramp up the sales. Well, this is not how it works, unfortunately. But we've been fortunate to get a few private individuals to pitch in on the project, and that also includes my retirement savings, to get the project going. And we hope after the demonstration of a conclusive single bubble fusion, raising subsequent funding won't be a big deal. So we did estimates of commercial viability. It's actually like 20-page document. Everybody wants to see whether this is commercial viable. So the bottom line is 10 kilowatts from 1 liter can be extracted. And the beauty of this process, there is no diminishing returns. So many good engineering ideas are killed by diminishing returns. You keep improving it, like internal combustion engine, spend 100% of effort, get 1% increase. Well, quantum mechanics that drives fusion turns this whole notion upside down. In fact, you raise your temperature 10 times, guess what? Your power raises 50,000 times. So this is engineer's dream. We increase the quality of the process by a tiny amount. We got huge reward in terms of energy, so that's what makes it beautiful. I'm gonna skip this. Just brief about our company. We're located in State College, Pennsylvania, at Penn State Innovation Park. No affiliation with university except that I work for Penn State, and which makes this beautiful too. I can do fusion all I want without risking my academic career or whatnot. So we have about 5 people working for us, some pretty cool equipment. And to conclude, I think I'm going to skip all of this BS. Basically, making the first step is the most difficult one, and I'm glad that we made this step. And things are looking optimistic. I'm happy to acknowledge a few people that contributed to making our experimentation possible. This is Ivan Kruglak, Ken Robinson of AECOM, Gary Zaremba, Asil Taksal, and now Mario Blanchet, that all shareholders of Quantum Potential Corporation that pitched in to make this work possible. And I feel pretty confident that, given 3 to 5 years, and assuming we can reach the funding goals that we have set forth, we'll be able to demonstrate a working prototype. And actually, maybe next year. Yeah. Let's strike a deal. So next year we'll bring a system here and we'll show how it works. So thank you.
Hey, we're right on time, but I think we can spare time for a couple questions if someone wants to come up. And by the way, if anybody has a spare $500,000, that might be a good investment.
Maybe you know the Russian scientist Nigmatulin.
Yes.
Yes, I worked with him in Russia, and when the laboratory in the United States was closed, he returned to Russia and continued such experiments. But now no support in Russia.
Exactly.
But in that period of time, I helped him because I'm a specialist in this area of cavitation.
Yeah, you're absolutely right. I actually met with Nigmatulin last November, and we discussed this project, and he was very eager, to collaborate because he believes it's the next big thing. And he carries some weight in Russia. He's the director of the Institute for Ocean Research. But what kills the deal is money. So to get his team engaged, you gotta have the money.
Max, please show formula number 5.
Okay.
Equation.
Oops.
No. Number 5.
Way back. You got a lot. Do you want me to just go to the beginning?
I'm almost there, I think. Is this one?
No. Is in no boundary continuum in this form, in this equation.
Looking for an equation.
Which equation? I didn't have any equations on this.
In your article.
Oh, in the paper. Okay. I don't have the picture of that equation.
What's the equation?
Не было, но здесь все. Sorry.
Okay. Sorry.
Witek, I'm Witek, and I'd like ask you about efficiency of this method, because thermonuclear neutrons can be obtained in many ways, in a way of plasma focus, tokamak, even with help of standard explosive materials. So the problem is not connected with obtaining neutrons, but with efficiency of this method. Could you say something about efficiency?
Yes, a good question. Basically, you can create thermonuclear fusion on the desktop. You can build a Farnsworth fuser, and you're going to get your thermonuclear reactions. You're going to get your neutrons, but you're not going to get a power source. So the question becomes, how can you extract power from the bubble fusion process? So what we're looking to do, we're looking for each bubble to produce about 5 to 10 nuclear fusions. Now, how do you make a lot of power? Well, with a high bubble density, by using 100 micron bubbles, we can have 1 bubble per cubic millimeter. Then a liter of liquid is going to have incalculable amount of bubbles, and when you make those oscillate, let's say at 30 kilohertz, you can produce 10 kilowatts from liter, and all you will need to run the process is about 1 kilowatt of acoustic power. So you get, 10 times excess power, theoretically. And that's, one of the objectives for our 3 or 5 year plan. So first we show single bubble, then we show multi-bubble, then we show control, that we can actually ramp up the amount of reactions to where it's sufficient. And fourth, we show that we can achieve break-even point to where we generate more power than we produce. So there are a lot of questions that need to be answered, and a lot of nitty-gritty detail that's going to come up. So I don't pretend to say that we have a magic bullet, but we have a plan that's efficient and fairly cheap to execute, and given the potential outcome, it's definitely worth it.
Excellent. Thank you so much. We're going to have a 10-minute break. We'll see you back.